We're now going to start a new chapter, chapter 11, on sequences and series. So to get started, let's talk about what a sequence is. A sequence is a list of numbers written in succession, and each number is going to be called a term. We are only going to discuss the infinite sequences in this course, although you have probably seen finite sequences before, and probably even infinite sequences. But in this chapter, we're only going to be looking at the infinite sequences. So let's take a look. This is the couple of different ways that they could be expressed. A sub 1, comma a sub 2, comma a sub 3. We are going to be focusing in on this n, the index of the sequence. So n in these definitions is defined as the index of the sequence. And we're going to use that index to write our sequences, to define our sequences. So unless otherwise stated, we'll assume that n is going to start at 1. If it's going to start at something other than 1, we'll indicate that in some way in the definition of the sequence. So just to get started, here we go. Let's take a couple of sequences and let's just list out the first 5 terms of these sequences. So if we've got 3 over n squared and we want to list out the first terms, we can do it in a couple of ways. If we wanted to, we could make a little table. We could start off by saying we've got n, it's not otherwise indicated, so we'll assume 1, 2, 3, 4, 5, and so forth. And then a sub n is going to be 3, and then 3 over 4, and then 3 over 9. We'll reduce that in just a second. 3 over 16, and 3 over 25. And so, of course, that guy becomes 1/3. And so if we were to want to list out the first 5 terms, we would list them out as so. 3 3/4, 1/3, 3/16, and 3/25. Now that doesn't end right there, so I'll just do the 3 dots here and continue it on. Okay, and if we wanted to keep going, let's just do another one. I didn't give myself a lot of space here, so let's move that guy down just a little bit, and then we can move that one down even further. Okay, so then on this one, if we wanted to start off, we've got a -1 to the nth power. Notice on this one that we're actually going to start at n equals 5. So if I were to want to list this out, and the table just kind of makes it easy to keep things organized. So n, and then the a sub nth term is -1 to the nth times n. Now this -1, and I'm going to officially define it here in just a minute, but this -1 to the nth power, when we do that, and remember n is this index, so we're starting at 5, 6, 7, our index is going to increase the counting numbers, the whole numbers here. So as we increase on the index, what's going to happen to that -1 is it's going to rotate between positive, negative, positive, negative. We actually define it as something called the switch, which I will do here in just a minute after we get through these first couple little examples. So if I've got n equals 5, then the first term here would actually be -1 to the 5th, so that's going to be a -5. But then as the index increases by 1, the next time I'm raising -1 to a positive, or to an even power, which makes it positive. So we get +6, -7, +8, -9. And that would give us the first 5 terms. So we can write that out: -5, 6, -7, 8, -9, and so forth. And we can see that for our sequence there. Okay. All right, and then on this next one, and I'm going to move this guy up just a smidge. On this next one, if I want to list out the first 5 terms, and I think I'll come over here and need a little bit more space here. So let's come over here. Actually, we'll do this. We'll end up writing the sequence down here, and let's write the table right here. Okay, so if we're, and this time we're going to start n greater than 2, so n is going to greater than or equal to 2. So we're going to start at 2, 3, 4, 5, and 6. And our term here has this 2n quantity squared on the top, and then it has this factorial, or n minus 1 bang. Again, I'll officially define that here. I have a definition down below that we'll talk about. But for that factorial, anytime we look at a factorial, so sidebar here for just a quick second. Anytime we look at a factorial, side note, when we're talking about a factorial, like n factorial, that is defined to be the product n times n minus 1 times n minus 2 all the way down to 3, 2, 1. Sometimes we actually write it the other way, like we start at 1, 2, 3, 1 times 2 times 3, up to n minus 1 times n. So for instance, if we were to say 5 factorial would be 5, 4, 3, 2, 1. Which of course, just properties of multiplication can be written the other direction. 1 times 2 times 3 times 4 times 5. Okay? Okay, so it's a quick little note on factorials here just to get us through this first example, and then we'll have the official definition of the factorials. But hopefully you've seen a factorial before. So back over here, so if we are looking at a sub n is 2n quantity squared over n minus 1 factorial, then for this first one, when n equals 2, we're going to end up with 4 squared on the top, and on the bottom we end up with 2 minus 1 in parentheses factorial. So of course we have to do the parenthesis first there. So we end up with 16 over 1, which is just 16. And then for 3, we're going to end up with 2 times 3, so we get 6 squared on the top, and in the bottom the 3 minus 1 factorial. So we've got 36 over, and then we have 2 factorial there, so that's going to be 36 over 2 times 1, and that ends up giving us 18. And then for the 4, we've got 8 squared on the top, and then on the bottom we've got 4 minus 1 factorial. So that ends up giving us, let's zoom in even more a little bit here so I have more space. So that ends up giving us 64 over 3 factorial. So we've got 64 over 3 times 2 times 1. And so that would be 32 over 3. And then for the 5 factorial, we end up with 10 squared. I'm sorry, for the 5th term, for n equals 5, we end up with 10 squared on the top, and we've got 5 minus 1 factorial, and that ends up giving us 100 over 4 factorial, or 100 over 4 times 3 times 2 times 1. Okay? And so that would give us a 25 over 6. And for n equals 6, and remember we needed 5 terms, but since we started at n equals 2, we'll go to n equals 6. That ends up being 12 squared over 6 minus 1 factorial, or bang is actually how we say that, kind of the short way to say factorial. 6 minus 1 bang, which is 5 bang, and we've got 144 over 5 factorial, so 144 over 5 times 4 times 3 times 2 times 1, and let's see there, so 144, that's going to end up being, let's see, let's reduce this, so 72, and then doing the 2, whoops, let's keep reducing, so and then another 2 would go into that, 36. So doing my canceling here, and then we've got 36, and then 3 would go in, so that would be 12 over, oh, and I can go in even one more time, so 6 fifths. And then we have our terms. So we can come back and list out the first 5 terms of our sequence here. So the sequence, this particular sequence would be 16, 18, 32 over 3, 25 over 6, 6 fifths, and on we go. So that would be the first 5 terms of that particular sequence. So we're going to be looking at these patterns and trying to determine what happens to these sequences as they head out towards infinity. So this is kind of an interesting one to start taking a look at. In the beginning, it looks as though it is actually increasing for a period of time, or for a period of terms. We look like we're sort of going up on those first 2 terms from the first term to the second term. But then notice there is some pattern here that is occurring where it is going down. All right, so then let's do a couple more little definitions here that showed up in our first couple of examples. I mentioned that when the sequence switches signs and changes from positive to negative on every other term, we can call that the switch. And so we're going to be needing to actually look at these sequences and write the explicit definition. We were given the explicit definition on the previous couple examples and then asked to write out a couple of terms. But if we have the terms and need to write the definition, and we see that the rotation occurs, positive, negative, then we know that we've got a switch. And a switch can be expressed as -1 to the nth, depending on if we want the sequence to start or if the sequence starts with positives or negatives. We can always change, the starting term, positive, negative, or get that change on the starting term with a -1 to the n or a -1 to the n minus 1. So the switch is something that we will definitely utilize. And then I mentioned, and I went through a quick little explanation of factorials earlier, but a factorial, or n bang, is defined as I've written here. And so we've got some examples down below I'll go through, but n bang is written as n times n minus 1 times n minus 2 all the way out to 3, 2, 1, or of course we could write it the other direction. So just as a quick little note, if you've got 5 factorial, we went through some factorials earlier, that's 5 times 4 times 3 times 2 times 1. And then we could calculate that out. Now, if we were to have n plus 3 factorial, then we start at n plus 3, and then we decrease down. So when we subtract 1, we would get n plus 2, n plus 1, and then we just continue on down, 3, 2, 1. Now, if we were to start at 2, or if we were to have 2n factorial, then what we do is we start at 2n times 2n minus 1. We always decrease by 1, 2n minus 2, all the way down until we got to 3, 2, 1. So factorials are a lot of fun, and we're going to play a lot more with factorials as we go. So let's keep moving on here, but we will definitely do more with factorials. Okay, so the next thing I want to do is I want to look at some sequences and actually write them as their explicit definition. So if we've got just the pattern of numbers and we want to write it with its explicit definition, I want to write this in terms of its index. So how do I do that? Well, some of them are obvious, some of them are not as obvious. And so how do we figure out these patterns is going to be our goal here. And what we can do here is we could make a table here similar to how we wrote out the first couple of terms, but this time we're trying to figure out the patterns. So if we have our index, and then we're trying to figure out what would be the a sub nth term. That's our goal over here. So if we just start the index 1, 2, 3, 4, and we can go as far as we need to. I don't think we'll need that many terms. This pattern is probably, some of you are probably looking at that and saying, I know what the pattern is already. But if we take our index here and then we just list out the terms. So the terms here were 1, 2, 3, 4, and so forth. Actually, we don't even have 5 on that term. And then if we can take a look at that, we can see pretty clearly how does that relate? How do each of these terms relate? How does each of these terms relate back to the index at that point? And we can see here that it was actually just the index. So the a sub nth term is just n. So we can define this particular sequence. We could say that this is the same as saying the sequence is just n. And we're assuming n starts at 1. If we wanted to, we could indicate it, but that's actually not necessary. So this part is assumed unless otherwise stated. Unless otherwise noted. Okay, we will assume we'll start at 1. So we could write it that way. Just another way that you could write it. You could, of course, say that a sub n equals n. That's another way to write that is the nth term. So you could write either of these. So here are just two formats that we could do. These mean the same thing. Okay. Now this one, so if we were to do this one, same thing. So we'll start off kind of thinking about what would be our pattern that we're looking for. So n, and what's the a sub nth term? So 1, 2, 3, maybe we'll go 4, and then trying to come up with what does that nth term look like. So if it's 1, -1, 1, -1, and clearly there's a switch here. And so as we're looking at this and we're saying, okay, so for the nth switch, well, the odd terms, based on the fact that I started the index at 1, the odd terms are even. So if the odd terms are even, and then this is going to be the switch. It's going to be -1, and there was nothing else actually besides the switch. So it's going to be -1. If I were to just put n on it, then this would actually return the opposite of the sign that I want, because if n is odd, just putting n on it would return a negative. So I need to either add 1 or subtract 1. And that part is really up to you. I'm going to say -1 right there. So I'm going to say this is equal to the sequence -1 to the n minus 1. But just some other possibilities, because there's all kinds of ways that this could actually be expressed. So there are definitely some other possibilities. So we could say, in this particular case, we could start with a sub n is -1 to the n minus 1, but that is exactly the same as saying -1 to the n plus 1. That would generate the same thing. So when I subtract 1 or add 1 on the switch, that's keeping with the same switch, the same switching pattern. Now, this is, of course, assuming that we're starting at n equals 1. So these all assume that n equals 1. These two possibilities assume start at n equals 1. Now we can play around with that as well, and we could start at n equals 0 if we were to have started this pattern. Now, again, we're the one deciding how we want to define this sequence here. So here's just another possibility. I just wanted to mention this, that if we had wanted to start the sequence actually at n equals 0, if we started the sequence at n equals 0, well, the first term in the sequence was 1, and then -1, and then 1, and then -1. And so if we had actually started the sequence at n equals 0, then this would have become -1 to the n. So notice that what that does, that shift, this is a little shift it's what we call a shift in the index. So we had a shift in the index here. And a shift in the index made a shift on, of course, on the power on the index as well. So a shift on the index, another possibility, and I'll do this one in red, another possibility would be to define this as -1 to the n. But this time we would say n equals 0 is our start. Okay, so this is what we get if we actually shifted the index. Shift the index to start at n equals 0. Okay, I want to do a couple more of these, but I'm getting close to the 20-minute mark on my video, so I'm going to go ahead and stop here, and then we'll pick up with some more examples and even get into the graphing. of these sequences and taking a look at what happens as we let n go to infinity. Look at some limits, actually get into a little more calculus here. Okay, there we go.